Can you guys see?
Yes.
Okay, good. So the topic of today is high performance computing with Python. This is the second Python workshop from RCC this semester. And we will probably try to continue from what we left off last time. I might do a little bit of replay, but shouldn't be take too much on. I wouldn't repeat it too much, okay? We have about like 50 pages of slides. If we finish earlier, we just go home earlier happily, okay? So motivation, so why Python? Again, I think I mentioned it before, I will be quick now. Also, I will introduce the Python resources at the RCC. Also, how to submit Python jobs to the cluster. I think I did everything on my own computer last time. This time, I will at least show you a few job submit scripts, say how to submit Python jobs to the cluster. Then I will start to talk about high performance computing using Python. This will be the major session for this for today's workshop. Also, I will talk about a little bit about the Python, say speed up Python code using Python. And I will talk a little bit about machine learning and the GPUs in the end. Okay, again, so why Python? Because it's relatively easier to learn compared with C, C++. The Python code is actually easy to read and to maintain. I want to emphasize one thing today is it have also relatively easier package management. Say, we do not want to reinvent the views. When we write our program, probably we are going to use what other people already did. So we are going to use in the libraries written by other people. But suppose you are writing C code or C++ code, you have to use other people's library. Sometimes to get your thing compiled can be a non-trivial task. Say if you are using a lot of library written by other third-party providers to get your packages managed in the proper way, isn't that easy? Say you might have your thing run on one platform. When you try to run your thing on another platform, you might be able to get it compiled successfully on one computer, but have huge problem when you go to another computer. So Python is much easier, typically, okay? So typically Python's package management is way easier than those compiled language. So there are the standard package management tool is called pip. There's another one I will recommend, which is Conda. So we can manage Python package using both pip, the virtual environment, and Conda has its own environment. So both are pretty good, okay? Yes, it's also kind of scalable. So we can parallelize it over a HPC cluster. So run your Python job on multiple computer nodes, okay? That's also possible. So this is the comparison between Python and C, C++. I think I showed this last time. Okay, so now it's a little different page. So yes, we want to use Python, but then when or why should I run Python on the HPC? It's quite easy to get Python installed on your own laptop. Then the question is when or why I would run Python job on the cluster. Here are the few situations where you might think you should run the job on the cluster instead of your own computer. For example, when you have a large amount of data, typically, I mean, people's laptop have maybe a few hundred gigabytes or like 1 terabyte. It's quite luxurious already, right? But if you have like a multiple terabytes of data you need to handle, at that time, your laptop, your own laptop probably is not enough. So RCC has a huge storage space for you, okay? We can help you to store many bytes of data if you need. Another situation is when you have a lot of computation. For example, if you are going to run a Python job, take say for about like 2 hours, usually I wouldn't run it on my computer anymore because if you have a laptop, if you want to run something for 2 hours, that means you do not want to do other things otherwise it's going to hurt the performance. Your computer, your laptop, you kind of like heat up pretty quickly. You will hear weird noise, right? Once you have thing needed to run like a couple of hours, I will start thinking about I want to offload my calculation from my computer to a remote computer. I don't even want to hear the noise. I just want to get the email when the calculation was finished, right? In that sense, it's it's the time you should think to do the calculation on the cluster. Instead, on your own laptop, you can use that as your computer for web browsing, for reading documentation, right? Or for even watching YouTube, but don't use it to do serious calculation. It's also, one reason is like when you want to benchmark your code. Say you want to see how your code really performs. In that sense, if you run your thing on your own computer, sometimes depend on what other thing was running, what other process are running, you get a different performance for the same code. Say you have the same executable, you run it for different multiple times, but each time you might get a different number. Why you start to think, why my code is faster or slower? In that sense, if you submit a job to a specific cluster with a specific computer node, you can benchmark your code in a better way. So you can get a more stable, you can get a stabler performance for your code, get some consistent performance or result when you try to benchmark your code. Another way, another time is like when you want to share your code or your data. Most people probably do not want to make their own computer like SSHable. You don't want to like store your data on your own laptop and allow other people to SSH and copy your data, right? So at that time, you might want to say, you store your program or your data on the HPC storage space, then create a group for it. Then only allow the people in your research group to read your code and share your data. In that sense, HPC is good for your job. Also, one case, like suppose you want to run some job which require a GPU, but the GPU is quite expensive. You might not have GPU on your computer, right? So, but the RCC does have like at least a few tens of GPUs free for you guys to use. So if you are a new user, you can create an account. You immediately get a 150 gigabyte of space, and we have some partitions for you to run job for free. For example, general access queue, backfill 2. You can start from reading documentations from the web link I provided, the RCC fsu.edu/docs. You can get a good start from there. Okay. Python resources at the RCC. So 2020 is the year when the Python community will formally stop supporting Python 2, but still we have Python 2 available in our cluster. So for quite a few versions of Linux operating system, I think they still have Python 2 there, okay? So we have both Python 2 and Python 3 available. We also have like 3 versions of Anaconda Python available. So we have 1 version of Anaconda 2 and 2 versions of Anaconda 3. For the 2 versions of Anaconda 3, we have 3.7 and 3.8. So in total, we have like 5 versions of Python for you to use. So you do have to figure out which one you want to use. And you do have to figure out how to find the correct Python version to use. In that sense, you load the correct module before you use it. Say, for example, if I want to use the Python 3, I just do a module load Python 3. If I want to do Anaconda 3, I just do a module load Anaconda 3. Okay, so you have to install other packages sometimes by yourself. The point is, yes, Python was built with like hundreds of packages already. And to make your life easier, Anaconda Python comes with another like a few hundreds of packages when you install it. But the thing is, even with that many hundreds of packages, you might still need to install packages for yourself. They're in particular for researchers, there are always new packages popping up. We don't have it. So you do have to install your own packages. That's why I want to start to talk more about package management using virtual environment or Conda environment. Say, here is a screenshot, say like how to deal with different versions of Python. So you can see when I run a which Python, so it shows the user bin Python. That's the system default, which is actually a Python 2, not a Python 3. If you want to use the system provided Python 3, I do a module load Python 3, then I run a which Python. You can see it's actually 3.7.0. Now, suppose I want to do anaconda Python. You can do anaconda. I can purge, clear what I previously loaded. I can do a module purge first, then load anaconda 2.7.15. Then you can see the path is anaconda 2, or you can do 3.7.3 or 3.8.3. So basically we have 5 versions of Python. You just find the correct one by purge and then load the correct Python modules. So again, the question. So first step. So if you want to use the Python on the HPC cluster, the first thing, you start with loading the correct module. You load the module, then you know where to start. But that does not mean that it's all set. Because even if with the Anaconda Python, there might still be packages it don't have. So you have to install your packages by yourself, right? So you load the Python module is only the first step. The second step is how about those other packages? You still have to install packages yourself. I do not want this to scare you guys away, because even if it's on your own computer, sometimes you do have to install packages. So it's not really much more difficult to install packages on the cluster compared with install packages on your own computer. They are essentially the same, just like looks a little bit difficult, but not really, okay? So on the HPC cluster, compared with your own computer, one thing I want to emphasize is, yes, you say, I'm ready to install packages, but then you quickly realize the system does not allow you to do so. Say, you are not allowed to install packages globally. Say, suppose you want to install some weird small packages, you want to install in the system directory, you will get a permission denied error because you are not allowed. As a non-admin user, you cannot install packages globally because we don't know if the package is needed by other people or not, right? So it's desirable for you to install package to your own disk space. Remember, you get a 150 gigabyte of space once you sign up for account. So you should install package to your own disk space. Then the question is how? And suppose I install more than one package later on, I might even get messed up. Where is my package? This does happen. Say, even if you are determined to install packages to your own space, you still need to figure out how to manage those extra packages you installed into your own disk space, right? Here comes the rescue. So we have this virtual environment and a Conda environment. So both ways will work. So the model for packages management is, for every your project, you should create a dedicated environment, okay? You might have more than one research project going on. Each of them might require some Python packages, right? So my suggestion is, for each project, create a separate Python virtual environment or Conda environment. So manage the environment for your project separately. This is different from like another kind of philosophy. There are people trying to say, okay, suppose you have a laptop, I install Python. Then the next thing you want to do is, okay, let's install all packages I might use. Say install immediate start to install like 300 packages. Then you think it's going to satisfy all your needs. That is one way to think. It's like make a really powerful single Python version with all packages. But that's actually not the recommended way. For example, suppose you get your software finished. You want to release your software. Now you need to tell your audience, your users, what packages are really needed for your software. You got stuck because you start with the Python with all packages installed. Yeah, it's powerful, but now it's difficult to do a clean cut. What are the packages really needed for that project, right? So in that sense, it's good to separate the Python packages required for different projects. And later on, it makes your life easier when you try to ship, release, or containerize your software. Say, suppose you write some Python software, you want to later on containerize it using tool like a Docker. At that time, you want to provide the user the really needed packages. In that sense, you do not want to do the way like you do not want to do it in the way that I mentioned earlier. Install everything you can imagine you might need it, then later on you don't know what are really needed, right? So for each of research project, create a dedicated Python environment for it. Then it makes your life easy to later on you want to ship or containerize your Python application. Okay, so are we good so far? I assume my colleague Alex did help me to answer question, okay? Because if I'm in the full screen mode, I didn't really see what people say. I assume people are question and are answered properly, okay? That's okay. So as I said, we have 5 versions of Python on the cluster. So you can create a virtual environment from any of these 5 versions of Python. But we have only 3 versions of Anaconda Python. So that means if you want to use the Conda environment, you do have to start from the Anaconda Python. So if you want to do virtual Python, if you want to do virtual environment, virtual env, you can start from either Python or Anaconda Python. But if you want to do Conda environment, you do have to start from a Conda instead of the system Python 2, system Python 3. You have to start from Anaconda Python to use Conda environment. I hope it makes sense, right? So I'm going to show some example for both virtual environment and Conda. And yeah. So here is a screenshot, a little kind of scary. So basically, let me show this later on, okay? I will show this later. So let's do, okay, so I hope you guys can see the terminal. I'm on the HPC cluster, okay? So this is the HPC login node. CD. Okay. Oh, sorry. This is a little scary, but it's not that horrible. It's just like I'm trying to be lazy, trying to organize the thing instead of type thing line by line. I can do it too. So basically what I'm trying to do is, if I already have a virtual environment called venv, I'm going to clean it first. If I already have a file saved all those packages I need, I'm going to clear those junk first. Then for the step 2, I'm going to load the Anaconda 3.8. Load the Anaconda is only the first step, right? I load the Anaconda, then I figure out which Python I am. Then I want to figure out which virtual environment I have. It must be the virtual environment from the Anaconda Python instead of the system Python, okay? Next, in the step 3, I'm going to create a virtual environment called venv. You can see here why at the beginning, step 1, I want to clear them first because I want to start with a new virtual environment. So I clear the junk first, okay? After I create a virtual environment called venv here, I activate it by running this source line, source venv being activated. So there is a script called activate. By running this line, I activate my own virtual environment. After that, when I do a which Python, which pip, it will show you the Python, the pip, in your own home directory. After that, I'm going to install a package, for example, called Django. Then I'm going to, because later I want to figure out what packages I really installed, I'm going to run the command called pip freeze and save everything into a thing called requirement.txt. How do I test I have installed my Django packages correctly? So what I'm going to run a single command to test the Django is installed by printing out the version of Django. Say I do a Python -c. -c means run some Python script just on the command line. I want to import the Django module and print the Django's version. I do a print with the parentheses because this is required for Python 3. For Python 2, you do not need the parentheses, but for Python 3, you have to do a print with the parentheses, call it like a function, okay? So yeah, let me explain again. I clear what might exist before I do anything. Then I load the Anaconda module to start with the correct Python version, then create a virtual environment. But there is nothing in the virtual environment yet. So I'm going to activate that environment and install a package called Django. After I install that package, I test it by running a single line to print the Django's version. Okay. Okay, you can see actually there is nothing here right now. So let's do a bash. It's a little slow to run on. You can see it's doing something, right? You can see it's downloading Django, right? It's going to install other dependencies too. Here I want to point out that I'm asking for only one package to be installed. Say I want to install Django, but the Python environment is smart enough to figure out what Django might require. Say Django might be dependent on a few other packages. So people will try to find those dependent packages and install those packages too. In that sense, it makes your life really easy. So you can see the output. The step 6, Django is installed. It prints out the version of the Django. We can scroll back to see what happened. Step 1, clean the junk. Step 2, load the Anaconda Python. It also shows me which virtual environment command I'm using. It's clearly the Anaconda 3.8 virtual environment. After that, I create my own virtual environment called venv. You can see here, the only difference, there are two differences, okay? One difference is there is a new directory called v. See here, this new directory is my own virtual environment, okay? There is also, okay, after I have my virtual environment, I installed a package called Django. The cool thing is that Python is smart enough to figure out Django require other packages, for example, PyTZ and ASG, whatever, I don't know what it is, and SQL parts. It automatically downloads those things and install it for you to help you to resolve the package dependency. I also want to save, like it install a few other packages, but how do I know? How do I know what packages I have installed? So I can do a this is basically what I put in the script, okay? If I run the command called the pip freeze, it basically tells you what the pip has installed for you. Say, I want Django, but it also installs 3 other packages for you. So later on, when you try to ship your software to your user, say you wrote some great machine learning or deep learning software, you want to distribute your work to other people, then you do not want to copy. You do not want to copy this directory to your users. Why? Because this directory was based on some Python, some Anaconda environment from your own computer. So if you copy this venv to your user, it won't work for them, right? So then what I'm going to do? So all you need is to tell them what are the packages installed. So that's what we are going to do. Say, this requirement.x just stored the name and the version of each package we need. So in that sense, you send your user your source code. you attach them with this extra file called requirement.txt. Then your user should be able to install those extra packages yourself. Do not try to release this directory called venv to your user because it only works for your own computer. I hope I make this point very clear. And I want you to see why the package management is essential for a good Python programmer with like an engineer's mindset. Okay, where we were. The conda environment, I'm not going to run it. The file is here, but I don't really do it again. I have too many condas in created already. Okay, create a conda. So previously, the previous example, I used the thing called a virtual env, right, to create a virtual environment. You can also create a conda environment using the conda command. For example, I'm doing essentially the same thing here, except 1 or 2 lines. For this line, I load. Remember, if you want to use conda environment, you have to start from a conda Python. So I loaded the conda module first. Then I run which conda instead of which virtual env, right? I run which conda, and it will tell me where is my conda located. After that, instead of run the virtual environment with the name of the environment, I do a conda create. So this is the essential different line. I'm going to create an environment called a Flask env. Create this environment. Then I want to activate it. I do a conda activate this environment. It's similar to your source space venv bin activate. I activate my conda environment. After that, instead of using pip install, I'm going to use the conda install. I install Flask into my own conda environment, then test it, print the Flask version. If you are done with that, you do a conda deactivate. That's what I did at the beginning. So they are essentially the same. So I'm not going to do it again. So, but I have the screenshot in the slides. If you are interested, you can ask me for the slide. And we do have you can see it here. One thing I want to emphasize is, you say, I create a conda environment called some name. Then the question, where is those things saved, right? Where clearly it's not going to save those packages globally because you don't have the permission to create a file into the system directory. So your files are saved in a hidden directory in your own home directory called .conda. I'm not going to run it because I think I have something already. So this is my own home directory, okay? Make it a little bigger. There are a lot of hidden directories. I think there is one called .conda. You see here, there is a hidden directory. In that directory, there is a directory called envs. Remember I told you earlier, for each of the project, for each of your research project, create a dedicated environment for it. It can be a virtual environment or it can be a conda environment. For example, this is what I have in my own directory. So in my own home directory, my username is bchance3. There is a hidden directory .conda. In that, there is a subdirectory called envs. In that directory, you can see there are like 10 environment in my own home, in my own hidden somewhere in my own disk space. This is what you are supposed to do for your own research project because this makes it very clean what packages are really needed for what project. For each project, you might create a good name for that conda environment. Then you know, okay, this is the environment I use to do that project or this project. Okay, remember, every project needs its own environment, either virtual environment or conda environment. Okay, here is a little comparison between virtual environment and conda environment. I want to say that virtual environment and the pip command, it's more like a Pythonic. This is what really comes with Python. But a good thing for conda is it comes with many packages already. And A bad thing for the pip is pip comes with a specific version of Python. Say, when you run pip, it's bound to that version of Python. But conda is powerful enough in the sense that suppose you have an anaconda Python with a specific version of Python, but you actually need a different version of Python for your project. You do not want to reinstall. You do not want to install a new version of conda. You actually want to create a conda environment. For that environment, install a dedicated version of Python. Say, you can even have a different version of Python in your specific conda environment compared with where you start with. But the pip, the virtual environment, is bound to a specific Python version. And the conda environment, it even allows you to install a different version of Python into that specific environment. So you may have the same version of Anaconda, but for different conda environment, it can run a different version of Python. In that sense, it's really powerful. For some packages, for example, PyTorch, I think conda does a better job in managing the package dependencies. If you log on, if you Google search PyTorch and try to install it, you will find the recommended package managing tool and the installation tool for PyTorch is actually Anaconda. So submit Python job to the HPC cluster. How to do that? If you want to run your Python job using RCC, you can do it in a few different ways. One way is most people start with, you run some interactive job on the HPC login node or the Sphere node. In that sense, for this kind of scenario, you would prefer to use the Sphere node, okay? Because HPC login node typically has many users. If you want to run big Python job there, it actually interferes with other people. So it's not recommended to do large Python jobs on the HPC login node, okay? For interactive job, you can use HPC login, but we recommend you to use Sphere. You can also submit batch job to the cluster from the login or the Sphere node. So this is actually the recommended way. Say, suppose you are working on some Python project on your own computer. So what you need to do is you do your testing, debugging on your own computer. But when you need to run some bigger runs, say take a few hours, at that time, you want to submit a background job, say submit a batch job to the cluster instead of just running on the login node, because the login node has other people using it, right? So it's not good to keep running Python job on the login node. So how to submit a batch job? Step 1, you write your great Python code. Step 2, somehow you have to copy the Python program from your own computer to the HPC storage, right? You have to move your code or your input data from your computer to the HPC login. Then there is one extra step. You have to write a submit script for Slurm. The resource manager and it's called Slurm for the HPC cluster. You write a small script. For people not familiar with this kind of scripting, we have some submit script generator by our colleague Alex. He's actually helping you guys to answer questions. He's author for the submit script generator. So if you are kind of tortured by this kind of thing, you don't know how to write this, we have a web page for you to create the submit script automatically, depending on which partition you want to submit the job to, how many cores you need. We have a web page to help you to create this submit script. So don't worry too much about this, okay? I hope I don't have COVID. But anyway, we are far away. Don't worry about it. I was coughing, okay, sneezing. Okay, so this is one example script. Say how I want to submit a Python job. So the previous one is called the great.py. It's great in the sense that you know which Python you are using. I do a module load Anaconda, so you are using the Anaconda Python. You always do a which Python here, I suggest you, because it's easy to get confused which Python I'm using, right? For all your submit script, you put like a which Python command, then it will print the Python path, then you know what you're doing. For this one, I call it greater.py. Why it's greater? Because I'm using my own virtual environment. Say, I have some virtual environment called venv. For this submit script, I first activate my own virtual environment. Then I run which Python. Then this Python is the Python sitting in my own home directory. I'm using my own virtual environment because I might have installed my own packages. That's why it's called greater. You don't really have to worry about the content of the greater. It's just like an imagined example for this workshop. But I want to see the progress, how we are going step by step forward by loading the correct anaconda module, step 1. Then create your own virtual environment, install packages to your own home directory. Then using those packages you have installed yourself. That's why we call it greater. Of course, we have greate.py. I don't have it. Okay. The idea is eventually you might want to like run your Python job over more than one computer node. Each node have multiple cores. For example, if I want to run the parallel job, which is running on 2 computer nodes, like 2 computers, each node has like 80 cores. This is the way you run it. I think for some job you don't even need the srun-n16. It's 16 because we have 2 nodes. Each node has 8 CPU, so say 2 by 8 is 16. But I think for Slurm, you don't have to put this number. It's smart enough to figure out by itself. Okay, HPC with Python. So why worry about the performance? I want to point out that Python does have its own disadvantages. Me, myself, is a Python lover, but that does not mean that Python is good for everything. Python code can be very slow compared with C, C++, or Fortran. Say C code can be like 100 times faster than Python code. So also there are times when you have really many data, you need it to be processed. So in that sense, if you're like, okay, the performance of my Python code is not good enough, right? So how to improve the performance? There are multiple things. More than one way you can try to improve the performance of your Python code. You can, if you are good at C, C++, you can try to speed up using C or C++ extension. You can also write parallel code using multiple threading or multiple processing. You can also try to use better hardware. For example, maybe I can try to run my Python job on the GPU node, right? A better hardware or better program itself. So you write a parallel program instead of serial program. For parallel, you can do multi-threading or multi-processing. Okay, these are 2 different things. I will try to explain better later on. You can also try to write some C code, figure out how to call my C code from Python. Say speed up using some C, C++ extension. This is the quick fix. Say I do not want to write any fancy parallel Python code. I just want to use the Slurm Job Array to do parallel computing. This actually works for quite a few people. In particular, for people, they have an embarrassing parallel job. See, they just have multiple data. They just have many batches of data they needed to handle. Say, you might just use this Slurm utility called Job Array without worrying about how to write parallel Python code. You can still try to distribute your job in a parallel way. Okay, so here is the example submit script. The idea is, say, I have my program called test.job.array.py, which use assume Python anaconda 3, but I'm not going to run it really in parallel. But the point is, I want this thing to handle different data. So it's the same program, but for each run, I want it to handle with the different data. In that sense, I do a Slurm Job Array. This Job Array, what it's going to do is, there are some trick. When I create a submit script, you see there is a S-batch -A 1 to 8. That means basically I'm going to submit this thing for 8 times, say from 1 to 8. I'm going to have like 8 clones. I'm going to run 8 clones of this job. with index like from 0 to 7. Each of them going to run on one node and one CPU. See, the point is, say, you can submit one job, do one thing, or you can submit 8 jobs, let them run like simultaneously. So this is basically what we are trying to do. I'm going to submit an array of Slurm jobs. Each of them is serial, but that might be all you really need, right? I submit array of serial jobs. Each of them is doing something different. Say, handling some different input, generate some different output. That's all you need. You just need to figure out how to submit multiple serial jobs concurrently, right? So here is my 3-line Python program. For example, I import the module called OS. That's the operating system module. From this module, I can read my environmental variable. What environmental variable I want to read? There is a Slurm environmental variable called Slurm Array Task ID. Remember, I create a task array with 8 tasks. So each of them get its own ID from 0 to 7. That number is critical because your Python code might simply be a big function call. That function call takes some input and generates some output. This Slurm array task ID will be the input it takes. So you create an array of array of Python job. Each of them get a different array task ID. You can use this as the argument you pass to your Python functions. So each of them handle a different task. In that sense, you can quickly start to parallelize your task by using Slurm Job Array without doing anything about parallel computing. You do not have to learn anything about parallel computing. You just need to figure out how to submit an array of jobs. Okay, where we are. For example, here is my array job. It's just going to read the parameter, my ID. The point is my ID will be different for each Python. So you might define some function great, which take my ID. So here is the key idea. By importing the operating system module, I can figure out which task ID I was assigned to. By using that task ID, you can call your function with different input or generate suppose you are doing some Monte Carlo simulation, you can use that as the seed for your random number generator to make sure you get a different simulation. Then you can run multiple simulations parallel. In the end, you just need to collect your result from different running, right? All you need is the pin, tell the job who I am. That's the Slurm array task ID. That's what it does. Say here is my submit script. The only thing is I want to see my job array, my array task ID, okay? Remember here, I submit my job only once, but you can see it generates a whole bunch of output in my directory. Why? Because I basically asked the Slurm scheduler to run 8 clones of my job. So you can see it has a different output with different name. In that way, you can quickly do your parallel computing using Slurm array. The key idea is inside Python, I got 2 for the one with array-2. For 3, you get 3. That can be used to decide which input directory you want to read, which input data file you want to read, or which output, what's the name of the output file. So this is a very promising way for new Python users who want to really use the power of the HPC, because you don't know how to write a thing in parallel, right? Then how I'm going to get some performance gain? You can use the Slurm job array to quickly start to run many things in parallel, okay? I hope I emphasized this idea enough. Now it's going to be more technical. So we have to wade through a little bit tough concept, but it's not, don't worry too much, okay? Because we have more than one way to do parallel computing. If you got stuck here, don't worry. We have other way to get things speed up. For example, threads and processes. Remember, we can do parallel computing by multiple threading or multiple processing. Then what's the difference between thread and process? This is actually what those computer science guys, those guys have a degree, really learn, okay? Threads are relatively lightweight. Process is heavyweight. So take more memory. So you want to create more than multiple processes. It uses more memory than multiple threads. And thread is shared memory based. However, processes are distributed memory based. It comes with some pros and cons, okay? If you are shared memory based, because we are accessing the same memory, so inter-thread communication is fast because we are accessing the same variable. For processes, because each of them have its own memory space, how to talk to each other is difficult. So you can easily create multiple processes, but how to send the data from one process to another process, say inter-process communication, IPC, is difficult. So ITC, inter-thread communication, is relatively easy, but inter-process communication is more difficult. But because it's shared memory, it's harder. Sometimes it's harder to coding, because if we have more than one thread trying to access the same data at the same time, it causes race condition. Sometimes to solve the race condition, you start to use a fancy thing like logs, semaphore, and it creates deadlock. In order to solve one problem, you create other problem. So, but let's not worry about this. Let those computer science guys worry about it, okay? So, one more page. This is from operating system concept textbook. This is a computer science textbook by Yale University, I believe. So, assume you have only one thread. You can think like a thread that just process. But for multi-threaded processes, each of them has its own core stack. Because you have different threads, they might be doing different things. So they must be using their own core stack. But suppose you have one file opened, so they can share the files, share the program, share the data. Say the resources, code, data, and files are shared by different threads. But each thread has its own registers, local variables, and its own core stack. So I'm going to run, I'm actually not going to run it because it's 350 already. I'm going to show you the result instead of directly running it. So I'm going to do one thing. Say, suppose I have a 1D array. Say I have a one-dimensional array, which is really huge. I want to find the sum of them. I want to get the sum of a huge one-dimensional array using Python code. I want to do it in the serial way, no parallel computing, or I want to do it in a multi-threading way, or a multi-processing way. So I will show you the source code, the submit script, and I will show you the screenshot of the output. So for a serial one, I hope you can understand this program. It's just like a 5 or 6 line. So I import the NumPy module called NumPy. So what I'm going to do is I have a huge for loop. Say, for I in this, you count how many zeros are there, okay? For I in this range, I computed the sign of this because the sign is a trigonometric function. It takes some time, right? I want to add some work to do. For this many iteration, I want to compute the sign, then add them. Then I print out the result. The time simply is like a clock. I put a stamp here when it starts. Then I run this huge for loop. Then I want to see how much time it takes to run. Here is a submit script. I hope this is not too difficult. It's just like a huge for loop. Each for loop will take the sign or something, add the result. It's like, imagine I'm adding a huge array. This is the serial version, okay? The submit script clearly I ask only one CPU, one computer nodes, and 10 minutes. It takes like a few minutes to run, okay? So my serial version is called example01 underscore ST. ST means like a single thread or serial program. Okay, Here is my threading version, multiple threading version. Let me go through it. So the package is called threading because I want to do multiple threading. So I import the threading module. I also import the NumPy. So the job, I create a function called a job. This is basically what I want my slaves, my workers to do. So job, take one input I. This I basically tell you from where to where I want to add the summation. Remember, I have like a many millions of numbers to add. This I basically tell my starting index and the ending index. Each job do a partial sum. After it's done with the calculation, it saves the result to the array called count. You can see here, I declare counts as the global array because counts is defined outside here. You see I have a counts array of the size equals to number of threads. So basically, I'm going to create a 4 thread. My number of threads equal to 4. For each thread, I wanted to do part of the summation. Remember, I have a large array to sum. I chop the array into 4 pieces. Each of them just do a partial sum. But each of them, after it gets its partial sum, it writes the result to the array of counts. In the end, I sum the partial sum. So I have 4 threads. Each thread do some calculation and store its result in one element of the count array. In the end, I found the total sum. So I sum the partial sum to get the total sum, right? So for the number of threads, I use the threading dot capital thread to create a thread object. Remember last week, I talked about the class object-oriented programming, right? So threading module has a class called a capital T thread. For this class, I'm going to instantiate, create a thread for each of the 4 threads I want to create. When you create a thread, you want to tell the thread what you want the thread to do. That's the first argument, target equal to job. Say, I want this thread to run the function called job, but this job itself takes one single input. That's the argument I. So I want to have the second parameter called args, which will be the argument you are going to insert into the function called job. So that's why things get a little bit confusing. I mean, you start to feel it's good if you understand a little bit about the functional programming. So when I instantiate the thread, I pass one argument called the target, which is job, which is a function. But this function itself needs a parameter. That parameter is what I'm passing in the args. That's the second argument. I create the thread, then call the method called start. This will tell the thread start to run. But later on, I want to save this thread first. I'll add a thread list to save the reference to all my threads. I have to wait for all my threads to finish. That's why I call it thread.join. If you do not call this join function, your main function might exit immediately. Say, it set out to run 4 threads. Each of thread might take a few minutes to run, but your main function finished, has nothing to do. Your code exited even without collecting the result. That's why you needed to call this thing called thread.join. Okay, thread.start tell the thread to start to run. Thread.join tell the main thread I have to wait for that thread. I have to join with it before I finish. Okay, the logic is a little difficult, but I don't have a better way to do it because I'm trying to do too many things in one workshop. I want to talk multi-processing, multi-threading, but honestly, each of these packages, threading or multi-process, each of those packages, they deserve their own workshop if we have a formal curriculum about parallel computing. Okay, threading, packages, multi-process, each of them can take many hours lectures. Okay, but today I just want to get an idea to know there is a package called threading. Okay, there are some class we can use to create a thread, let it run. Okay, so the idea I think I emphasized already. You just need to have that memorize. There is a package called threading. This package has a class called thread, and there is a method thread.start, thread.join. If you have this put this in your memory, it's good enough for today. Now, how should the submit script look like? This is a little bit scary, okay? You can like shocked. Why I need like 4 scripts to submit that threaded job? Actually, you don't need. You do not need a 4 submit script. I create a 4 submit script because all of them failed. It's not working. Okay, this is kind of surprising. Okay, so you can run it in the Python without srun. You can call, you see, just look at the last line of each of these 4 pictures. We have Python EX01, we have srun Python, and we have a similar passrun Python, but srun with -n1 -c5. See, I'm adjusting how I'm going to call this program. It's the same multiple threading code, but I tried a different way to call it from the Slurm job scheduler. So we have like -N1, -lowercase n5. I also have this -N1, -lower n1, -C. That means CPU per task. Because I know it's a multiple threading job. So instead of using lowercase n equal to 5, maybe I should try lowercase c equal to 5 because it's a threaded job, not a multiple processing job. You might got really confused, but don't worry. You don't have to memorize any of them because none of them actually work. So this is what I got, okay? This is a screenshot. I'm not going to run it because we are kind of tight in time. All 4 attempts failed. You can see the performance. All of them is like a 180 seconds or something. So my serial runtime for this run is like 200 seconds. So all those parallel things, I didn't really see any performance gain, okay? Essentially the serial version 1. You get like confused or even get angry or mad why I'm sitting here listening to this guy talking about parallel computing, right? So this is what I learned when I was trying to learn parallel computing in Python. So I suffered as you because I tried so many different ways, read like 4 script, try to see some performance gain, but it does not give me anything because there's a thing called a global interpreter lock, okay? The point is you start the 4 threads, but it's only 1 process that we are calling only 1 Python runtime. Say, Python is the interpreted language. When you run the Python code, you need to call the Python itself. The Python itself has a lock. Only you have 4 or 5 threads running, but at one time, only 1 thread can use that Python runtime. You can see the problem. Say, I'm trying to run 5 things parallel. Then all that 5 things need to use Python runtime, but only 1 guy can use that runtime at one time. So this is what we call a global interpreter lock, or GIL, G-I-L, or GIL, okay? This is like a more advanced software engineer job interview question, okay? So what is GIL? It's hard to understand like in 3 minutes. It's probably good for you to go home and do a little bit of Google on some Stack Overflow website, read some paragraphs, see why it's not any faster. Other people have similar performance as me. You can see from, this is the screenshot from Stack Overflow, okay? So now, multi-threading doesn't work. Let's try multi-processing. So there is a similar package. Instead of threading, it's called a multi-process. So it's essentially the same thing. You can see the job. I create a method called job. This is what I want the process to run, but it has 2 parameters. Set it I, that's what we saw before, and the sender. You don't have to understand the program, but the idea is, compared with the previous example, I created 4 threads. I'm going to create 4 process. You can see here in this 4 I equal to range NaN task. I create a pipe. Pipe is the channel between 2 processes. Remember, different processes have its own memory space. So how do I send the data to another process? So Python has a fancy thing called a pipe. Imagine pipe has 2 ends, right? A pipe. 1 end for read data, 1 end for write data. So I create 4 processes and also create 4 pipes. So each of the processes do something, do some calculation, and get some number. In the end, it's write the result using the pipe, the sender. The sender means the the writing side of the pipe. Each process do the calculation and then insert some data into the pipe. But for the main process, so the main function who is calling those, who is creating those processes, who is on the other side of the pipe, who is going to collect results from all 4 pipes. It's kind of crazy, but if you program in another fancy language like Golang, Google's Golang, it has a Go routine and a Go channel. Golang's Go channel is kind of similar to Python's multiprocessing module, similar to the pipe thing. Okay, the Python's pipe is conceptually similar to the Google's Golang's Go channel. I hope I didn't confuse you too much, but the idea is I create 4 processes and essentially let them do the similar thing. Then how about the performance? Before I tell you, before I show you the performance, I want to memorize the package name is called multiprocessing. Inside the multiprocessing, this shouldn't be thread, okay? This should be process, okay? To create a process, the method is called a process. Remember, we have a module called threading. We have a class called thread. Now we have a module called multiprocessing. We have a class called process. Similar to thread join, thread start, we have a process start, process join. They are very similar in syntax, but at least we get a performance gain for the, we can get a performance gain for the multiprocessing one. See, this is my submit script. I just have 1 version, the first version I run. So I have only 1 version of the Slurm submit script, okay? I just wrote 1 version. It works, nothing fancy here, it just works. This is the performance again. Remember, for the serial version, it takes like 180 seconds or something, but for my process, for my multiprocessing one, when I run in the serial, I get 167 seconds, but if I run the parallel, the multiple processing one, I get 39 seconds. 39 over 167, it's about like 4 times faster. We actually have like 5 processes, but the 1 process is the master process. 1 process is assigning jobs and is creating the other 4 processes. So essentially, it's only like 4 guys doing the job. 1 guy is the commander. So the performance is not 5 times faster, but it's close to 4 times faster. So you can see the difference between threading and the processing. Okay, so for those guys trying to do parallel computing in terms of using Python, so this is the thing you want to take home. Say, threading, remember, is subject to or is suffered from the global interpreter lock issue. You might spend forever without getting any performance gain, depending on what you're doing. But threading is useful if you are doing concurrent job instead of parallel job. Multiprocessing, at least for some reasonable job, it works pretty nicely. Okay, so there is also another third-party library called MPI for Pi. This is the MPI binding. For those guys who are good at MPI programming using Fortran, C, C++, you might want to directly start with MPI for Pi. But for users, for relatively junior Python users, you do not learn MPI, or you never program in C, C++, I would not recommend you to start with MPI for Pi. You might want to start with, say, multiprocessing. And you can also try multi-threading. Okay, I would point you to multiprocess first. Okay, if you are really good Python guy, you might want to do MPI programming or using MPI for Pi. We don't have time to talk about MPI for Pi today because I want to do a little bit of Python before we end up. Okay. I want to see, are we really totally confused? Okay, I just want to see like the chat. Let's move on with the Python. Okay, so Python. So why is Python slow? So what is Python? I want to show you some very quick examples, okay? So why is Python slow. Remember, Python is dynamically typed. Everything is an object. You consider how number 1, an integer, is stored in C compared with how it is stored in Python. See, for C, it probably just take like a 1 byte, 2 byte, 4 byte. But for Python, it's stored as an object. The object has a header, and the real data is hiding somewhere in that object. If I want to do, say, A equal to 1, B equal to 1, I want to do A plus B, Python have to get into that Python object to figure out, okay, that's an integer. Then get into the detail of B to figure out it is an integer too. Then finally know the plus means you want to add 2 integers instead of concatenating 2 strings or concatenating 2 arrays, right? There are so many possibilities for this plus sign, right? It plus can be overloaded to do very different things. So that's why Python is slow, okay? Also, Python is not a compiled language. It is interpreted. So if you write a C code, you use a compiler, for example, GNU GCC, you compile it to get output immediately. You get a binary code. Binary code always run quickly. But if you are running a Python script, so you write some text file trying to run it, you shouldn't expect to be as fast as running a binary, right? Binary is always way faster than running some script. Okay. Python also have like a inefficient memory access. For example, I have a list A and B, but each of the element has different type. So when I do a for loop to do AI plus BI, for every time of this, every iteration of this for loop, it needs to figure out what I'm adding. Am I adding 2 integers, 2 float, 2 strings, or other thing, right? In that sense, it is slow. And those numbers are stored in different regions of the memory instead of contiguous region of the memory. That's why it is slow. So what is Python? Python is actually Python with some static C data type. For example, this is a 2-line Python code. I define a function called func, func. It takes 2 parameters, A and B. I'm going to add them. I think I showed you this example last week. But the point is, I emphasized already, this plus sign can do different things depending on what A is, what B is, right? However, if I want to be faster, I can write a Python code, essentially the same, except that I annotate the type of A to be an integer, the type of B to be an integer. I also make it clear the returning type of this function is int. You see the difference? For A and B, I put an int, means they are integers. I also tell you the input type is int. I use this keyword called cdef, means the C definition. I'm going to return an integer, and the input are also integer. So you can see it's essentially the Python code, but with explicit type. For my input argument, for my output, I also make it clear what's the type, integer, float, or string. Python code has extension .pyx instead of py. I want to point out that Python you can consider as like a new language. So you cannot use the Python interpreter, say directly run Python name.pyx because Python don't understand those cdef thing, right? So it's kind of like a new language. You cannot directly run it using Python. Then how to run it? So the typical way is you write your Python code first, create your .pyx. Then you want to convert or translating your Python, you want to translate your Python code into C code using the utility called Python. Say there is a package called Python. You can use pip install or virtual environment to install Python. If you use Anaconda Python, it already comes with Python. So you can use Python to translate your Python code into a C code. After that, you want to compile your C code into a module. After that, you import it. This is quite scary. So for example, I read some Fibonacci. I defined a Fibonacci function, using Python. I have to do several steps. First, translate Python Python code into C code, then compile C code into an object, then try to import that object from your Python code. This is very scary for new user, because for new user who may never do any software compilation, he does not know how to install a compiler, how to translate the code, how to compile code, and later how to import the code. It's like this logical step was kind of overwhelming. You can do it on the HPC cluster, but I want to show you something dirty today. So we have IPython, interactive Python. IPython actually supports Python natively. Say, if you use IPython notebook, you can save the many pain. It's going to, you just need to remember two magic commands. For IPython, there are two magic commands. There is one called the %sign load external. So sorry, load extension. I'm going to load the Python extension. That's one magic command. Another is this double %sign Python. So I will show you example how it works. Don't worry too much. Okay. So okay, so I'm on my own computer, not on the HPC cluster. So this is my own computer, okay? So which Python? So I have Anaconda 3 installed on my own computer. So I'm going to use IPython instead of Python, okay? You see IPython notebook. So I have a IPython notebook file called quick Python tutorial. Okay, I want to make the font bigger. Okay, remember I mentioned there are two magic commands. First is the load the Python extension, load ext Python. Nothing happened here. I'm going to use the Fibonacci sequence as a simple example. For those guys who don't remember, it's like starting from 1, 1, then the next one is the sum of the two previous ones. So every number, starting from the third entry, every number is the sum of its two previous entries, okay? I define a Fibonacci, define a function called fib. So if n less than 3, return 1. Then if not, then I have a for loop to keep adding them, return the last one. I hope you have no problem understanding this thing, okay? Then, let's not do it here. This is the second version. I want to see the magic, okay? I call it a fib1. Remember, I have a fib, which is purely Python. I'm going to create a second Fibonacci function called fib1, which is actually essentially, literally the same as the previous one. They are exactly the same, except at the beginning, I have the second magic command, double %sign Python. This is the same Python code, but with this double %sign annotator there. What we will do is it will try to compile this Python code into C code, even if it's the same Python code. I'm going to create a C version and run it. That's the difference. I'm not going to run it right now because I'm going to run it in the end. So this is another step. This one is called cfib. This time, I'm going to make only one change. I'm going to annotate the input n to be an integer. This is essentially the same as the previous one, except that I make the input parameter n, I make it clear it is an integer. So this is my third version of my Fibonacci function. Okay? This is another version. This is again another version. You can see for those local variables used in my function, I call it a cfib2, okay? For the input, I make it clear it is an integer. But inside my function, I have internal variables, say local variable a and b, right? I declare all of them as integer. So from no type to with input, I put a type. Or furthermore, for those internal variables, I also declare its type. So I'm just adding more and more type declarations into my Python code, right? So that's really what I did. So basically I have a pure Python code. That's first version. And pure Python code, but just converted into a C code. And again, I have started to have Python code by making the input n, declare it as an integer. Also, I also have one version to declare every variable I use, say a, b, I, n, all of them as integer. So this is the full version I do. Now the question is, how does the performance different, right? Let's see what we can get. I'm going to, the Python has a magic command called time it. Time it will run it for enough many times and take the average, then tell you how fast each version run, okay? So you can see for the pure Python function, fib, if I computed the Fibonacci function with input 10, it takes me like a 650 nanosecond. However, if I run the second version, just use the Python compiler, it get like it's twice as fast because now it's 317 nanosecond. If I declare the first argument n as integer, it goes to 121 nanosecond. If I furthermore declare the internal variable a and b and I index I as integer, I get 43 nanosecond. So 650 divided by 43 is about 15, right? Think about it. You are writing some Python code, running it on your own computer, right? And by just doing some Python magic, say load this extension and annotated some key part, some CPU intensive part of your function, declare those variables as integers, float, you can see how much speed up you get. See, from 650 nanosecond to 43 nanosecond, it's a 15 times speed up. Imagine something previous to run, say 2 hours. Now you can finish it within 5 or 6 minutes. How does that feel? Okay, that's what Python can do for us, okay? We also have another package called PyBending 11, which is more difficult. I didn't have a chance to cover today, but you know, I'm done with this little Python example, but I only scratched the surface, okay? I run it on the IPython notebook. For those students interested in data science, machine learning, I would say like start with Anaconda Python and use this IPython notebook and think about the Python. Because you can see I only changed my code very slightly. I get like a 15 times speed up. For a simple function, for a function as simple as the fib, I get a 15 times speed up, okay? So let's get back where we are. Okay, I think I show you all of this code already. Essentially the same code, but adding more and more tab declaration. Then we get a pretty good performance gain, like what I showed you before. Okay, so a little about the machine learning and the GPU. So we do have more and more like a student in data science running fancy package like a TensorFlow or PyTorch on the HPC cluster. They are also very aggressive. They all want to use the GPU actually. So what the GPU resource we have on RCC? So we had the older one. We started from Tesla 2050. That's the Tesla GPU, not the Tesla car, okay? We start from Tesla 2000. Now we have a GeForce 1080 Ti. So the computer capability jumped from 2.0 to 6.1. I think we have the architecture of the hardware go from Fermi to Pascal. So the CUDA compiler version go from 6.5 to 10.1, I believe. So we have computer node. We have a few computer node. Each node typically have like a 4 GPU card. And the computer nodes are also big memory nodes, say with like 256 gigabyte memory. Those are pretty big. These 250 gig are memory, not hard disk, not disk, okay? 250 gig memory is pretty luxurious, okay? Typical on your laptop, you have like 8 gigabyte or 16 gigabyte, probably for a student. But our computer node, the GPU node, has 250 gigabyte of memory with 4 GPU cards. So I think for graduate students like doing some testing run for their machine learning, deep learning code, these are pretty enough for you to finish your dissertation. Okay, if you need to run some very CPU or GPU intensive job on the cluster. Okay, here is the examples script. This is old one because this one is loading Anaconda 3.6.5. This thing I used probably 1 year ago. But anyway, I think I stole this script from a graduate student because I didn't write this digital recognition Pi. It's a friend's script, not mine. But you can see that's how they do it. The essential line is for S batch. There is one line --GRES. This line tells the Slurm scheduler, I want 1 GPU, okay? I want 1 computer node, but for that specific node, please give me 1 GPU, okay? This GRES means generic resource. What resource I want? Besides CPU, I want 1 GPU. If you write your script this way, your job will be assigned to a computer node with a GPU. Remember, not many nodes have GPU. So you have to specify the requirement explicitly to get a GPU node. That's why you need this --GRES line to get a node with the GPU. Okay. Here is the summary of what we did today. I think I'm almost done. So we have like, remember, for the research computing center, we have 5 versions of Python. I talk about how to install packages. Say do a package management yourself using either the virtual environment or the Conda environment. I also tell you how to submit Slurm Python job. In particular, how to do a how to submit an array job, a Slurm array job. For those guys who do not know how to do parallel Python computing, you can use Slurm array to do simple parallel computing. I also talk about multi-threading. Remember, there is a killer called a GIL. That's the global interpreter log. I also show you example of multiprocessing. I didn't have time to really show detail, say try to explain the logic of the threading package and the multiprocessing package. But at least I want to see for the multiprocessing example, I can get like a expected speed up. I also give you a very quick introduction to Python. Essentially for Python, if your calculation is big, you really need to compile your code into a C module, then try to import it from Python. But I cheat a little bit by using the IPython because IPython directly supports Python. So in that sense, you don't have to figure out how to compile or translate your Python code. You can directly get some speed up using the IPython notebook. That's all I have for today. I think I'm going to quit here. Okay.
All right. Thank you very much, Ben.